in the previous class, we were talking about the various structural systems that we can make using masonry units, bricks, isn't it? Right? So there were, before that we had talked about some famous buildings and other structures that are made with masonry, and then we started talking about various kind of structural systems that can be made with masonry. So the two obvious structural systems are columns and walls. That is where masonry have an automatic advantage, right? So these could be made with clay bricks, it could be made with stone bricks, and so on. Then we were talking about other type of structural system, which is known as flexural structural systems, right? So it could be a beam or a slab. In such kind of spaces, you also want to use bricks, because there was a time when bricks were the only type of structures or only type of structural system that were available to the mankind, right? There was timber also. So sometimes they used to use timber in combination with bricks to span long distances, uh, long spaces. But the problem with masonry is that almost all kinds of such kind of materials, whether it is concrete, whether it is masonry, whether it is mortar, all these materials, which are basically earth-based materials, they have very good compressive strength. So you take a brick, you can apply a load of a truck on a brick and nothing happens to the brick, right? A truck's wheel can very easily pass over a brick and nothing happens to the brick. However, if you apply even 10% of that load in tension on that brick, the brick would very easily fail, right? And as you know, flexure is made of tension and compression. So part of the brick is in tension, a part of the brick of that part of that brick is in compression. So the part that is in tension would fail, and as a consequence, the brick would fail. And that is what was observed when they started using large size bricks over a space. So for example, when they wanted to cover a span a distance, let's say as a lintel. So this is a typical lintel use, right? All these applications are lintel. So for example, here you have a window, and above that window, they wanted to make a lintel. So if they wanted to put a single brick unit, finding a brick unit that is of that size was very difficult. So your doors and windows were very narrow. And also the bricks were susceptible to tensile cracking. So you used to have this kind of a tensile crack developing. The crack that you can, I have marked a few lines here. Some kind of a tensile cracks would appear here. Yeah, and that's where the brick would fail in tension. Then people thought, okay, a single brick may not be sufficient. Well, how about two bricks? And we arrange them in such a way so that they work as a truss. And I had discussed that last time also. So these bricks, these kind of form an arch, and such kind of arches were known as primitive arches, right? So basically, you put two bricks touching together in such a way so that they behave like a truss rather than an arch, but you can call them an arch, but essentially they are truss elements. Yeah. The requirement here was that these two brick units, they would want to slide off. So you had to put some kind of an anchor here so that it does not slide off. So you had to put extra heavy weights on at the two ends so that the two bricks don't slide off, right? As long as they were able to accomplish this, the two brick units could be used to span any space. However, still the amount of space that you could span was very limited, even with this arrangement, right? So they had to figure out a better way to do this. One other arrangement they were working with was known as corbelled arches. In this corbelled arches arrangement, again, you would put bricks and at a step. So if you look at this image at the bottom, in this image, if you see, at every layer, as they move up layer by layer, at every layer, the brick is protruding outward a little bit from the lower layer, right, on both sides. So the layer above has a brick which has the bricks that are coming out a little bit, and then so on and so forth, and it keeps going until the space is covered. And the trick here was that the brick, the overhanging part of the brick is smaller than the part that is anchored from the backside. So there is a part that is counterweight on the backside, and then additional weight is there. So for example, if you look at this brick here. So it has a little bit of overhang, but then it has a big counterweight, and that counterweight is also carrying some other additional weight, and as a consequence the brick remains stable. And this kind of arches were quite common in India. Okay, so basically so far you have seen, if you ignore the first type, which is basically using a single brick unit as a beam or lintel, then you have two types of arches that we have seen so far: primitive arches and corbelled arches. But these are not fundamental types of arches, or like that in the true sense. These are not really arches. Arches became very popular in the Europe, and some people, their origin is kind of disputed, because some people in the Islamic Arabic world also claim the credit for arches, but the oldest arches can be traced back to almost 3,500 years back. Yeah, so these arches, at the time they did not understand the mechanics, but they were able to, with trial and error, the engineers at the time were able to figure out that if they put bricks in a particular fashion, in a curved shape, then they were able to avoid any tension. And tension is what you wanted to avoid. Basically, the entire arrangement, even what we saw earlier, it's basically the tension in the brick that leads to failure of the brick. So they were somehow able to avoid that much of tension, and they figured that if they put these bricks in a circular fashion or in a curved fashion, then they were able to avoid that tension, the development of tension in the brick. So they did not really understand the mechanics at the time, but through experience they had understood that, and that's what they were using. So basically they did not exactly know the shape also. So ideally, if the load is uniformly distributed, the shape has to be parabolic, right? And I will do this derivation quickly, where we will see that a parabolic shape provides you perfect, no tensile kind of stress state. However, they were going with sometimes hyperbolic, sometimes circular, sometimes parabolic. Also, it does not matter exactly that you have to be in that shape. So for example, here you can see this is a door opening, right? So there is a door, there's supposed to be door here, and this is the opening for that door. And as long as, and theoretically parabola should be the line where the load should be applied, or the arch should be shaped like a parabola. Now what they have done is they have provided a thick layer of bricks which is shaped like a semicircle followed by straight lines. But as long as they are making sure that that imaginary parabola always lies within that compression zone, then they can make sure that the system is stable. There might be some minor tension developing somewhere, some cracks may appear, but that will not lead to any failure. Okay. However, if they go for very thin semicircular arch, then there might be a possibility that this parabola, the imaginary parabola, is going beyond the limits of the arch, and in that case you may have a situation where you may develop too much of tension, and there may be failure. Okay, so you may notice here, especially in the arch portion, they are using bricks which are not really rectangular, right? They are wedge shaped. These are not really rectangular shape. These are wedge shaped. The angles are not 90-degree angles. Yeah, and these kind of bricks were very commonly used up to even after independence. I think some structures I have seen which were built after independence, and even in such cases, such kind of bricks were used. Yeah, but now these are very uncommon. It may even be difficult to find such kind of bricks in the market now. Okay, what is the reason why arches are not very common these days, are not very popular these days? In the last class I had talked about a little bit. What is the reason why we don't see so many arches in the modern construction, but we used to see a lot of arches in the earlier construction? Anybody? I'm waiting for an answer. I'll repeat the question. The question is, in the earlier days, we used to see a lot of arches, right? So if you go to any older structures, you go to any old mosques, Taj Mahal, for example. So if you look at Taj Mahal, the dome is curved like this, right? And the doors, Buland Darwaza, for example, or any of the older days, any doors, if you see. One answer is Likhit Kumar has said, use of masonry has decreased. We need to utilize the space. Okay. Yeah, so there are advantages. I understand that. So if we make an arch, then it won't be useful. Yeah, so I understand, but yeah, Sarthak is correct. So Sarthak is basically given, I mean, all of them, all of you are correct. Sarthak is saying that steel is more utilized now. So earlier, when they were using masonry, they were not using steel with it. Later, they learned to use steel with masonry, and then they stopped using masonry and they moved to concrete, but still they have to use steel with it. So the answer is steel. Basically, in the earlier days, they did not know how to use steel with masonry, and as a result, they did not know how to span, how to carry tension, right? Once they learn how to use steel with other materials, it could be masonry, it could be concrete, whatever that material is, that is good in compression. Once they learn how to use steel with it, then they were able to use it with masonry. So the concept of lintel was not there. But now they could simply provide a flat element, straightforward plain element, wherein they can the element itself can carry tension as well as compression. So steel was the major invention. It's not that they did not know that steel existed. They had not figured out how to use steel with these materials so that they did not have to worry about tension. Okay, fine. So there were many structures available all over the world. You can see in India, mostly I think Muslim influence brought arches to India. Pre-Muslim era, we don't see many arches being used. What we see are more like primitive arches, which are more like trusses. So if you see old temple architecture in India, you would see they have this triangular kind of a conical kind of a shape, which is not really an arch in true sense. And with the with Islamic and with the Arabic and the Turkish and Middle Eastern and what is that area, Central Asian influence, that when that influence started coming into India, then we started seeing more and more arches being formed and domes being formed. Okay, so arches are a very effective way, very effective tools to span long distances. You can see some of the largest structures of the earlier times, they were made using domes or arches where you don't have to provide any intermediate supports. Okay, all right. So I've been saying that for if you use arches in a way or true arches, then you don't have a requirement to provide any tensile any material that can carry tension. So basically there is no tension. So I'll do a quick derivation for your reference so that you can see for yourself that that is really true. So the example that I'm taking here is of a 3-hinged arch. This is a very common type of an arch. For a very long time, they did not know how to use a 2-hinged arch, so they used to use a 3-hinged arch. So this is a 3-hinged arch. Why am I calling it 3-hinged? Because there are 3 hinges here. There is 1 hinge at each support, and there is 1 hinge right in the middle. Okay. If you don't use that hinge in the middle, you can still use it. The only issue is that then this structure would be an indeterminate type of structure, and analysis will be slightly more involved. It can still be used as long as you don't introduce any inbuilt stresses. Okay, so in order to keep it relatively simple, I have not left the dimensions as abstract. I have actually fixed the dimensions. So anybody has a question? Somebody is saying something. Unless you want to ask a question, please mute your mic. Okay, so if this is an arch and this is a parabolic arch, okay, parabolic arch. So in a parabolic arch, I have given some finite dimensions instead of just writing A and B. So the span that this covering is about 40 meters, and the total height I have taken as 10 meters. Okay, and there is a uniformly distributed load W acting on this arch. Now you must notice that this W is uniform in horizontal space. It is not uniform over the length of the arch. Okay, and that is a very clear distinction that you have to make. Okay, so if there is a W weight acting at a unit horizontal dimension, then what we can see is that we can very easily develop the equation of this arch if we count our x from here, we assume that this is our origin, and we can count our x from here and y from here. So y in terms of x can be written as x square by 40, isn't it? Y is equal to x square divided by 40. How do we know that? Let's say when x is 0, y is 0, that is true. And when x is equal to 20, x square by 40 will be 400 by 40, that is 10. So y is 10. All right. Similarly, you can also write, assume that x is going this way, and then you can write the expression for this side of the arch. So let's what I want to do now is I want to know anywhere along, so anywhere along the length, is there going to be any moment, any bending moment, right? That's what I want to know. And I assume that all of you have taken mechanics courses, so you should be familiar with the concept of bending moment, right? So I'll go step by step. Basically what happens here is that whatever load is applied, the total length is 40 multiplied by W, right? That is the load applied. 20 plus 20, that is 40 multiplied by W. That is the total load acting on the arch. Now for that total load will be resisted at these two supports. So let me name them. Let me name these two supports. These two supports will be called A, B, and C. A and C are the two supports, and the intermediate point, that is also a hinge, is B. Okay, so if I draw the free body diagram of the complete arch, this is the arch ABC, and then ignore these lines, please. The load is W, that is distributed over the entire length of the arch, and some reactions will be acting at supports A and C, correct? How will that those reactions be? Those reactions will be in such a way so that the entire arch is in force equilibrium. Agreed? So if I can write the force equilibrium equations here, the vertical reactions will be balanced by vertical force, and horizontal reactions will be balanced by themselves. So XA plus XC will be equal to 0. Agreed? There is no other horizontal force acting on this entire system. So XA plus XC will be equal to 0. And YA plus YC minus 40 times W is equal to 0. Now you may know, because this is a symmetric structure, YA and YC should be equal to each other, right? If we do moment balance, we will be able to figure that out, but I don't want to do moment balance. So YA is equal to YC, because this is a symmetric structure. So the two reactions should be same. So if that is the case, I can know what is YA. YA is equal to YC. So 2YA is equal to 40W. So YA is equal to 20 times W. Okay. Is that okay? But I don't know how much is XB yet. Okay. So let me do some. Let me do some moment balance here. So if I take moment about point A, so this was sigma Fx is equal to 0. This is sigma Fy is equal to 0. And I'll also do a moment balance. So from moment balance, sigma MA, M about point A. Okay. So what do I get from here? XA, YA I won't get. I'll have to look at external force, that is, and that has to be 0. That means 40 times W multiplied by distance 20, right? So that is clockwise, moment, minus YC multiplied by, sorry, I think I'm making a mistake here. No, that is not really required. Okay, please skip this step. I don't need this step right now, because it will essentially give me the same information, moment balance. I cannot get the values of XA and XC from here. I have to work at the half arch. Okay, so YA is equal to 20 times W. Now, if I look at the half arch, so basically what I've done is I have first solved the free body diagram of the entire arch. Now I've taken half of the arch. Okay, only this half. So in this half of the arch, in this half of this arch, there are again 4 possible forces possible, right? Because at each end, here there is a hinge and here there is a hinge. So no moment is possible, that we know for sure. There is no external moment possible here. There is no external moment possible at A, and there is no external moment possible at B either. Fine. So these are the only 4 forces possible: XA, YA, XB, YB. Out of these 4, I know YA is equal to 20 W. And how much is the vertical load acting? 20 W. Total 20 W. So YB will be equal to how much? 0. Is that correct? Because 20 W is acting vertically downward, 20 W is acting vertically upward. So the two will balance themselves. So YB will be 0. What is left? Horizontal force reaction. So horizontal force reaction will tell me XA plus XB is equal to 0. These are the only 2 horizontal forces acting, right? Now I want to know what is XA and what is XB, and I'm not getting that value from here, from this equation. But what I can do now is I can do sigma MA is equal to 0. I can take moments about A and balance that to be 0. What does that give me? It gives me 20 times W is the total force. This total length is 20. 20 multiplied by W is the total force. Its centroid is at 10 distance. Its centroid is a distance 10 from point A. So 10. So that is the moment clockwise direction because of load W, plus XB multiplied by, what is that distance? It's 10 meters, right? XB multiplied by 10 minus YB multiplied by 20 is equal to 0. Now we know that YB is equal to 0 already. So that means my XB is equal to, how much will that be? Minus 20 W. Is that correct? So that means my sign of XB was wrong. XB is actually acting in this direction. Right? So XB is equal to 20 W acting in opposite direction of what I had plotted. All right, so now I want to know what is the moment, bending moment at any given location in the arch. I have calculated forces at the 3 locations, at the hinges, but I don't know forces anywhere along the length of the arch, and that's what I want to know. And I want to make sure that that moment should be 0, right? That's what I've been claiming, that bending moment anywhere is 0. If the bending moment is 0, that means tension force demand is 0. So how do we do that? We will take a portion of that arch. Okay, so that arch, it had a point A somewhere here, correct? I'm not marking that point now. Erase that. Okay, yeah, somebody's mic was working. Okay, there are a couple of questions. I think I'll get back to them in a minute. Let me complete this derivation. So this arch was extending this way, which I have from that I have taken a small portion that is x long. Okay, so ignore that part, please. And here I know the reactions. There is no vertical reaction at this point. We just calculated that yb was 0, and xb was calculated as 20w in this direction. Right? So that is what it is. So xb is given as 20w, and I do not know what are the forces at location x. At this location, I don't know what are the forces, and I want to calculate those forces. Okay. So what I can do is, and in addition to that, there is this W distributed load that is acting, external force. Okay. So what we will do is, we will assume that there are three forces acting at that location. There is an axial force acting in the axial direction, that is Px. There is a shear force acting in the perpendicular direction, that is Bx. And then there is Mx moment acting. We will say that, let's say there is a moment, and we will try to figure out how much that moment is. Now we know from that, from Newton's first law, that for this system to be in equilibrium, all the moments on this system should, summation of all the moments on this system should be equal to 0. So which are all the moments acting on this system? First is mx, that is in counterclockwise direction, and I'm calculating moment about point x. Okay, so mx, that is counterclockwise direction, plus w times x. X is this distance, so w times x is the force, multiplied by at what distance? At what distance is it acting? At x by 2 distance is the centroid of this force acting, minus, now this 20w that is acting in the, so sorry, mx and component wx are acting in the clockwise direction, and 20w is acting in the counterclockwise direction. So 20w multiplied by what distance? So if this distance is x, I can call this distance as y. Right, so this times y, and that should be equal to 0. Anybody has a problem with this? This seems okay, right? Right. So, and initially we had seen in the very beginning that y was equal to x square by 40. So for any unit x, you can calculate y. So I substitute y value here. Mx is equal to, I'm just putting the terms to the other side, 20 times w times 40, sorry, x square by 40. What do I get? Wx square by 2 minus wx square by 2, isn't it? That is 0. So basically what it tells us is that moment is 0. And why were we able to get moment as 0? Because our y was following this profile of x square by 40. Y here, this y here, sorry, this y here y was following this profile of x square by 40. Only because of that we were able to get the moment, 0 moment. So hence we are able to prove, I mean, of course this is not an absolute proof. I mean, we had of vertical to horizontal span was 1:4, but you can pretty much pick any geometry that does parabola and loads are distributed. You would get similar kind of behavior. Okay, so let me go back to the questions that some of you had asked. Can we say 3-hinged parabolic arch is same as 2 bricks which are kept in slant position? No, absolutely not. The 3-hinged parabolic arch is the hinge in the middle is not really playing any role. Even if you did not have that hinge, and somehow you are because you guys might not have taken the courses on determinate versus indeterminate structures yet, or you may not have the understanding. 3-hinged parabolic arch is a determinate structure, and that's why it is possible for me to solve it in this class. If it were not a three hinged, if it were only two hinges, one hinge here, and then this arch, okay, and there is a continuous arch, still it would have same behavior. Okay, the only problem is that I will not be able to solve it in this class. It will take too long to solve. There is it becomes an indeterminate problem, and you have to do displacement compatibility and all those things. Which were kept in a slant position, that was a completely different problem. What was happening there was that these two bricks were there, and as long as you did not have any loads acting here, the system behaved in complete compression. But what was happening was that in reality you would always have some forces acting here, and if that is the case, that did not really have it. So these bricks were actually in flexure, in actually they were carrying moment, so they were not really truly behaving as arches. But anyway, they were an approximation. In other words, what you can say is that if you go for a single node, then you have a very crude arch. If you go for two nodes, then you have a more sophisticated arch. If you go for 4 nodes, 6 nodes, 7 nodes, you have more and more closer approximation to an arch. Just like you can think of, let me give you an example. If I need a thread actually for that, give me a minute, I'll get a thread and I'll tell you exactly what happens. Or maybe I can draw it. Let me draw and try to explain. Let's say I have a thread. Let me get at least one thread to start with. Okay, so what, here I have a charging cable. Actually, it's not really a thread. Okay, all right, so here is a thread, and let's say this is a thread, and now of course this has very large stiffness. This wire has a decent stiffness, and therefore you don't see a perfect parabolic profile. But let's say you had a cable like this, and you hang some weight in the middle. Yeah, so assuming that I'm holding it two different places, and I hang a weight in the middle. Yeah, so these are the two different places, and I'm hanging a weight. How do I hang a weight? Okay, the weight is very small, but still you can see. So now what the shape that you got is one of the primitive arches kind of a shape, because if you have a perfect only single point load, then it is a primitive arch. It's basically a truss, two straight lines. But if I put three different weights at three different, one right in the middle, and two here and one here, I'll draw these. So for example, if I have these 2 points of support, if I have these 2 points from where a cable or a wire is hanging, and it would be hanging like this on its own weight. But if I put a load here, then what would happen? This will change its shape to a triangle, right? And that's where the weight will be hanging. But what happens if I do this? If I apply 2 more weights here, then the shape I'll get is right, which is polygon sort of a thing. With 3 weights hanging. Agreed? And if I have more and more weights, then again it will become very similar to what it was originally, a parabola, where the load is acting everywhere. Okay, so that is what a parabola looks like. Now in this case, this is an inverse of an arch. Everything is in tension, right? You can switch this thing completely, put it upside down, and you can use this same geometry where the loads are acting this way, uniformly distributed loads. But now everything is in compression. Okay, so cable cannot be used, but masonry kind of material can be used where everything is in compression. I hope that answers your question, right? Okay. All right. Okay, so we'll move forward very quickly now. So that's how it proves that arches could have been used as a system where only compression would be acting along the length of the member, and then you could span long distances. You can make openings for the doors, you can make big domes out of these arches. Now domes are not really parabolic in shape. So as we had discussed, any other dome, those domes are not really parabolic in shape. So as we had discussed, depends on the thickness of the dome. So if the thickness of that slab that is used for the dome is sufficient so that you can draw an imaginary parabola inside, then also it will do. Plus all these materials always have some tensile strength also. It's not like they have zero tensile strength. All of them have some tensile strength. So even if a minor tensile stress develops somewhere, that is not always a problem. Okay. So we will now move to hardcore masonry lectures. Okay, so masonry, as you know, are made of two types of materials. One, you need a masonry unit, which is known as brick. The other thing is the component or the material that joins them together, right? So that would be some kind of a mortar or some kind of a paste. So first we will talk about, most of the discussion will be about the masonry units. Then we will go into the discussion about the mortar and how the masonry works as a combined composite material. Okay, so the masonry unit, the bricks, they can be classified into various ways, and we'll go into classifications. First, we want to get familiar with some of the common things that appear with masonries. Okay, so if you have a typical masonry, here the first picture, here if you can see, there are three dimensions. So the largest dimension is usually known as length. The second largest dimension is known as width, and the third largest dimension is usually known as height. Okay, so let's say if I have a brick of size 9-inch versus 4-inch versus 3 inches. Okay, 9, 4, 3. So 9 would be the length, 4 would be the width, and 3 would be the height. Okay, length and width is obvious, but height, which one to be placed at height? So smallest one is usually called height, and based on this, then the different surfaces are also named. So the surface that is between the length and height is called face. The surface that is between width and length is called top, and the surface that is between the width and height is called end. Okay, any questions, doubts? This is straightforward, right? So these are just the names that are given to different faces and different edges and so on. Now, you may have different types of geometries for the bricks. So based on the geometry of the brick, they can be classified in various ways. So the most common types of bricks are either solid bricks or cored bricks or cellular bricks. Okay, so cored bricks are the ones where you have a core passing through the brick, and oftentimes these cores are used. There can be a couple of purposes. Can anybody guess what would be the purpose of a core, of providing a core in a brick, which is basically a hollow space? So you have all the material around this core, and this core is hollow, and mostly it is through hole. You can unmute your. Somebody's typing the answer. Steel rebars, steel rods. Yeah, steel rods. Sometimes steel rods are used for this course. That's correct answer. But even when they are not used, still it has some utility. Anybody else? Weight reduction, yes. So very good. So basically what happens is that often you have a brick thickness, and for that thickness you still want you don't want to reduce the size of the brick, but oftentimes you realize that if I make a solid brick, completely solid of that size, then it will be too heavy, and really I don't have very high strength requirement. And sometimes if you cut cores from inside, you remove some material that will still give you large dimension, but with reduced net overall density, which may be good for you. So that's why they cut the cores. Also, core helps with thermal properties, because if there is a void in between, that brick is generally a relatively good heat conductor, or earth is also a decent heat conductor, but these voids kind of create insulation. right? So whenever you have some kind of insulating material, so these air voids kind of create insulation. So there is another advantage. You may also have some kind of a embossing sort of a thing on the surface of a brick, right? So this is very, very common for clay bricks. All of you must have seen some kind of a engraving on the surface, right? And this engraving is usually known as frog. What is the purpose of this engraving? What should be the use of this engraving? You can see this, right? In the third picture, there is some kind of a depression on the surface, and sometimes you have plain depression, sometimes you have brand name of the company who makes these bricks also embossed on this one. What is the purpose? Interlocking. Yes. So interlocking is, I mean, it should not be really called interlocking, because for interlocking to work, the other brick should have an opposite of this depression. So one brick should have this depression. The other side, the brick that is going to sit on top of it, should have that much of protrusion, that much of protrude some part of brick protruding outward. It will fit into this, but that is not really the purpose of frogging these frogs. This really, I think you are just you understand the concept, you're just not using the right words. It helps with developing a bond between the mortar and the brick, because usually if you have a perfectly flat surface for the brick, the bond between the brick and mortar may not be as good. So it helps with development of that bond, and also it helps them provide the brand name. Yeah. Hollow unit for flat ends. So this is often used. You may have two types of hollow units. Hollow units with the frogged ends, where you have a hollow unit. So the purpose of making the brick hollow is still the same. One is insulation. Second one is to reduce the weight for the same dimensions. So sometimes you may cut a core, and sometimes you can make a very large cell inside the brick. So the material, a lot of material is taken out, and that's how you form a cellular brick. So for a cellular brick, you may have a geometry. Sometimes you have frogs, so that you can, the next brick will come and sit in next to it. And sometimes you may not have a frog, and you may just attach bricks side by side. Both types of bricks are quite commonly used. Now, what is the difference between cell and core? They are essentially serving the same purpose, but a cell seems to be very big in comparison to core, and you are right. So if the void, that is the area or the volume of that hollow area, if it is the cross section area is of one void is less than 1.5 inch square or 960 millimeter square, then it will be called a core. Otherwise it will be called a cell. So a cell is a bigger core, that's all. Yeah. And there is a limit that they have set. And sometimes what happens is that you have a brick, that brick has some cores, but the cores are not really very large. So basically total sum of all the cores is not really more than 20% of the entire brick surface area. And if that is the case, then you don't have to use, so then that brick will not be classified as a cored brick, but it will be classified as a solid brick. And what will happen is that whenever you have to use the brick surface area, there will be some classification requirements later. So there you would use the entire cross section area or entire surface area rather than just the net area. However, if the cores are than 20% of this area, so this is the total area. Of this total area, the area of the cross section area of the cores is more than 20%. Then it will be called as a cored brick, and in that case, for any calculation for the cross section area, you have to take only the net area, and you have to deduct the core area from the total area. Okay. Now, based on the shapes, there are 3-4 classifications, and also bricks can be classified in 3-4 different categories based on the material that is used. So the most common types of bricks that have been used and are still being used are burnt clay bricks. The burnt clay bricks are the bricks that are made with clay, but then they are burnt in a kiln. We had discussed about this last time. So basically you take some mud, basically, which is clay mixed with water and some other minerals. That is the mud that you take, and then you put them into a mold or use some kind of a mechanism to form a cuboid kind of a shape, right? Using that material, and then you let it dry, then you let it burn at very high temperatures, and that's how you get a burnt clay brick. These are the most common type of bricks. Then you may have some sand lime bricks, which are not as commonly used nowadays, but in certain areas where there is lime is abundantly available, these bricks could be used. Lime is also has some adhesive properties like cement. So it, once you mix it with water and then water dries up, it hardens, it develops significant amount of strength. So these don't have to be burnt, they can have sufficient strength. Okay. Then concrete masonry units. These are the most common type of bricks in urban areas nowadays. In urban areas, clay bricks have become very uncommon, because partly because the excavation of clay is very difficult nowadays. So, and then kilns are, they produce a lot of pollution. So because of that, kilns are also not appreciated these days, and therefore these concrete masonry units. So these are basically sand mixed with cement, and maybe some other stabilizers are added with water, and you let the cement harden, and as a result you get a unit which is made of concrete. Okay. Then you may have building stone, which is basically some kind of stone. It could be red stone, sandstone, limestone, which is basically taken from a quarry. It could be granite. So have you guys noticed any stone walls in IIT Hyderabad campus? Are there any stone walls in IIT campus? Anybody? Have you seen any stone walls in IIT campus? No? No stone wall, huh? Nobody has seen? You guys have not come to IIT yet? IIT Hyderabad I'm talking about. Anybody else? There are a number of places where stone walls are used. In academic block B. Stone wall in academic block B. You're surprising me now. Academic block A also stone walls. No. Where in academic block A? Maybe you can unmute your mic and tell me.
Sir, in that second floor.
In the second floor? No way. No, that cannot be the wall. I think you're misunderstanding something else as a wall. And it's mostly concrete. There is anyway, the boundary wall of IIT Hyderabad. IIT Hyderabad has a large boundary wall, right? And most of it is made of stone, granite stone that they have used. Okay, and even some of the utility rooms. So if you, there is a big, there are actually a few places where they have put generators, and not generators, I think these are mostly transformers and those kind of things. So these are used for as a power substation, and many such structures are there. If you drive along the main boulevard, the tech boulevard of IIT Hyderabad, you will see some such structures, and some of these walls are also made of stone. Okay. In academic buildings, I don't think there is any stone used for as a wall. I mean, for pavement it is used, but that is called cobbled pavement, cobbled stone pavement. But that is not what I'm talking about. I'm talking about stone walls. So only the boundary wall is the major structural component that is made. Structural, non-structural, whatever you want to call it, a component that has used stone. Okay. Based on appearance and shape, you can call them solid bricks. So a brick can be solid brick if it is completely solid, or otherwise it has to have the cores or whatever cells. They should not be more than 20% of the total volume. If they are more than 20% of the total volume, then they are not solid bricks. Then they come into perforated or cored brick category. Yeah, that is the second category, either solid brick category or the second category. Then you may have cellular masonry units. So hollow or cellular masonry units are usually the ones which are extruded using a facility. I'll show you a video in a minute. And then you may have spatial shape bricks. These are very uncommon these days. So you may remember when they were making arches with bricks. Those arches were made of bricks which were not really square shaped. The edges were not at 90-degree angles. They were at a different angle. So those bricks used to be of a different classification. Earlier they were very common, but nowadays it would be very difficult to get such kind of bricks. And then plinth bricks were also different types of bricks, which were, so sometimes some bricks would have slightly different shape based on the application, and then they would be classified like that. Now, as far as clay bricks are concerned, there are three commonly used methods for making clay bricks. One is handmade method, right? And this I have, it used to be very common, most common way of making bricks. I think in the North India, still that way is very common. But the second method that is used is stiff mud method. So this is more mechanized method, which is also quite common nowadays. And the second method is becoming more and more common in comparison to the first method. And the third one, dry press method, it is relatively uncommon, but with this method you can get very high strength clay. Okay, what is the difference between the three methods? The difference is whether how much water you can add. So in the first method you have to add much more water because you are operating by hand. So basically what you do is you add some water to bricks, so that the photo that you see here is from the first method. So basically what you do is you add some water to clay, so until it becomes soft, and usually you have to add approximately 20 to 30% of the water of the total weight of clay. That's quite a bit of water that makes clay very soft. Okay, and then you put that clay in a mold. So the mold could be made of some kind of a wood or some kind of a steel item, steel plates. You put clay into that mold and you try to compress it by using some kind of a semi-mechanized system. You can press with hands, you can press with some kind of a mechanical system. Compress that clay into that mold so that the clay takes that shape of that mold. And then once it takes that shape, you remove the clay from that mold, so you get a square shaped or whatever cuboid shape brick. But this is still very soft, and very carefully you'll place it under the sun so that it dries. Once it dries, also you have to make sure that, because there is so much of water in this clay, while drying there is a chance that clay may deform, right? So you have to make sure that your clay is of exact right quality and it has all the minerals in the right proportion, so that the deformation and that cracking is not too bad. Okay, so once it dries under the sun and it gains some strength, then you take this brick and put it in a kiln. Inside the kiln, it is allowed to burn for several days and several weeks, and once it comes out of the kiln, it is very hard, solid brick. Okay, however, the second method, which is stiff mud method, which is more mechanized method, the problem with the hand operation of this kind of a, so basically in this one you have 12 to 15% water, so you use less amount of water. When you use less amount of water, you can mix clay very well with some kind of mechanical system, but after you mix it, this clay is very stiff. So since the clay is very stiff, it is very difficult to operate with hand, and therefore filling a mold with this clay will be very difficult, and making it take the shape of that mold perfectly without leaving any cracks or any corners is very difficult. So therefore they have to go with a mechanized method, and one video is shared here. I will show that video in a minute. So this kind of a method, the advantage is that since you use less water, okay, what happens to the water in the first method? For example, you had 30% water, let's say. So you had 30% water. Once you burn it inside the kiln, what happens to that water? Evaporates, right? And that water was, those molecules were still sitting, were earlier sitting in the inside the brick. So those spaces that were occupied by the water before, what happens to that space? That turns into air void. That means there are small voids all over that brick, and that means that the brick has less strength. However, if you have less water, that means after that water evaporates, you have less number of voids. That means you have higher strength. Okay, so using less water is better, right? But the challenges are there, because if you use less water, the mud will be very difficult to work with. So you cannot, it will not be very malleable. So you cannot make it, you cannot very easily force it to take different shapes, and that's why they have to use mechanized systems. Okay, so in this case they don't use mold, because mold requires a lot of malleability. So what they do is they use some kind of a extrusion. So let me try to play one of the videos which will show you how it works. Ignore the advertisement for a minute. Okay, so for example, they are taking clay from the ground, then they are putting it all in a mixer. They are adding some water. This is a mechanical mixer. It mixes it, right? And after mixing, it forms, see, it comes out from this mixer as a slab of mud. And since it is, it's kind of an extrusion system, and it operates under a very high pressure, um, it will be very difficult to do it manually. But since it's a mechanical system, mechanized system, they are able to achieve this kind of a high density brick. And then what they do is they cut this into slabs, right? So these slabs are of decent size. This is not a brick size. They cut them. They use some kind of a wire to cut it. So then they get a shape of this length, and then they pass it on to another platform. So it is relatively stiff. It is much stiffer than a held than a mold kind of an operation. And here they have several wires, and they put this big slab in front of them, and then again they use a machine to hydraulic press kind of a thing to press it against those wires. So once this entire slab gets pressed against the wires, it cuts them into regular shapes, and that's how you form the bricks. Yeah, that method is clear, right? So this was the die here. This is the die from which the brick slab is coming out. Okay, so it basically takes the shape of the die. Okay, here in this kind of a system, it is very easy to provide a core. So in this die itself, you may have a small blockage in the middle. So if you had a blockage in the middle, that's where you will get a core. So it is very difficult to get a core in a mold system. In a mold, you may get a frog, but in this kind of a brick, it is very difficult to get a frog because you never have an opportunity to create a frog, right? It comes out, and then you simply cut it with wires. There was never any opportunity to create a frog on the surface. But while you are doing the extrusion, at the time of extrusion itself, if you have a kind of a some kind of a small piece of metal, or a number of such piece of steel metals, which will block the flow of clay in that area, so you will end up getting cores. You will end up getting hollow spaces there. Yeah, in this particular example, they don't have any cores. This is solid brick, but you may have cored bricks as well. Okay. Okay, going back to the presentation. Oh, we are already. When does our time end? 4 p.m. Right? Yeah. Okay, so we have some time. Okay. So the first one was the hand-operated one, which is handmade soft mud. The second one is stiff mud. The third one is dry press, wherein this is very similar to the first operation, which is handmade soft mud. But then here the molds, the clay, soft clay, which is mixed with water, it is placed inside a mold, and then a hydraulic press is used to give it the shape inside the mold. So mold, you can't have this hand operated kind of a mold. It is done under a very high stress, and under that kind of stress, they are able to push it uh, and give it the shape. So this requires very little water, but the machine required to do this kind of an operation is also very heavy duty. It's not very commonly used. In some places nowadays, it is. You can see it being used. All right. So these are the three different ways in which you can form clay bricks. Now, the soft mud that you use in these clay bricks, it has to have certain properties. Okay. So one obvious property is that when you are operating with that soft mud, it should be malleable so that it takes the shape that you want it to take, right? So it should not require too much of water, because there are two ways you can get malleability. You can get this flexibility in the bricks. The flexibility without having to add too much water, and that is desirable, right? Because if you add too much water, you actually lose in strength. So what you can do is, ideally what we need is, it should have more malleability, plasticity during the when it is wet, but after it dries and after it becomes hard after burning, then it should have high strength. Okay. Generally, for a good malleability and good high strength later on and durability later on, some minerals are required. So the most common mineral that you need is the silica, right? What is silica? What do you understand by silica? What is the chemical formula of silica? What is silica? SiO2, right? So SiO2 is and which mineral or sorry, which how is it found in nature? Sand, very good. So sand, clay, silt, they are all basically silica. So if you take a grain of sand or if you take a very small particle of clay, they are all the same essentially. The only thing that is different between sand and clay is the particle size. Okay, and they are all silica. Okay, so obviously you need silica. So in your clay, silica should be at least 50 to 60%, and that is the main constituent of your clay mud. In addition to that silica, you should have 20 to 30% alumina. Okay, and alumina is quite abundant in nature, and you should have about 20 to 30% alumina. The alumina has this property, and it provides this malleability to break during the wet period when it is soft and muddy. Okay. Now, if the clay that you're using has too much alumina, then it will make it very difficult to handle because it will be too malleable. So then you should have to limit the amount of alumina available in the clay. In addition to that, there should be some lime available. So if it is not, if some of these minerals are not naturally available in that clay, then you have to add them uh, separately. So if lime is basically mostly your calcium compounds, calcium oxide, calcium hydroxide, calcium carbonate, and they actually help silica fuse. Why does silica fuse? Silica is basically what happens is when you heat it at a very high temperature, these silica particles start to fuse under, like, they come in contact with each other and they fuse. And once these particles start to fuse, they form a single unit of the entire brick. So all the silica particles start to fuse together. Not all of them fuse, but still they form a network of silica. And as a consequence, you get a single unit. That's how you get the strength. Okay. Lime helps this fusion process. Okay. Iron oxide also works as an assistant. So some iron oxide should be present, which will help lime in the fusion of silica. Some magnesia is required. Magnesia actually helps with reduction of shrinkage. So shrinkage is a bad property because what happens? Shrinkage takes place when the water is drying up, right? So you take the brick, you take the mud unit that has come out from the mold, which has a lot of water, and then you let it dry under the sun for a couple of days. During that period, water evaporates. As the water evaporates, the cavities start to collapse. The cavities where the water was stored, they start to collapse, and as a result, the brick starts to shrink. And if it shrinks too much, then it can lead to cracking in the brick. Okay, and the sizes change. So that shrinkage is a bad thing. We should try to minimize the shrinkage. So magnesia helps minimize that shrinkage. Okay, there are some materials which could be available, which could be present in the clay, and we should try to minimize or eliminate them. So alkalis are bad news. Iron pyrites, FeSN, Fe and sulfur together, they are also bad things. They lead to, basically what we need is an amorphous kind of a matrix of silica, and if iron pyrites are present, then they will lead to crystallization of that, and that will make it very the brick very brittle. Okay, it will become very brittle, will disintegrate very easily. So iron pyrites are not desirable. Alkalis are not desirable. Okay. Any organic material, of course, is not desirable, because organic material means it will burn when you put it in the kiln, and it will leave a cavity inside after burning. and that cavity will be the weak spot. Okay, too much of CaO and calcium and magnesium oxides are not good. Any soluble materials are not good. What happens with soluble materials? If there are any soluble materials, let's say there is some kind of a salt that is soluble, what is the harm with that? The problem is that these soluble materials, after you put the brick in a building, it will get exposed to water over a period of time, right? So once it get exposed to water, these soluble materials will dissolve. Yeah, so this soluble material will dissolve, and then water, after a period of time, let's say that water evaporates, then these dissolved salts will come out to the surface and get deposited there. And over a period of time, after several cycles of wetting and drying and wetting and drying, this will lead to big cavities forming inside the brick, which will make the brick weaker. Okay. Now, I had mentioned 50 to 60% of the brick is basically made of silica, right? Now, silica can be found in three forms, in three different sizes. It could be in form of clay, it could be in form of sand, it could be in form of silt. The difference between sand, silt, and clay is only the size. So there can be, here in this slide, you can see on this scale, you can see the particle size in millimeter. So sand can vary between about 5 millimeter size. It's 1, 2, 3, 4, yeah, almost 4 millimeter size to 0.0405 millimeter size. Okay, so of course for making the bricks, you don't need very large very coarse sand. You may need some fine sand. So approximately 30% to 50% sand can be used, and the largest chunk should be from clay and silt, that is smaller than 0.05 millimeter. Okay, so 0.05 millimeter is 1/20th of a millimeter. Okay, that's a pretty fine size, and about 50% or more should be clay, and between 30 to 50% should be sand. Okay, so these are the desirable constituents of a masonry unit. So I think I can stop here today. We are not able to get much of discussion in this mode of teaching, and I feel like I'm continuously talking. So any questions, folks? Okay, one question is, are the percentage by weight or volume? These are by weight. Any other question? Okay, so maybe I'll just complete this slide and then I'll carry on with the next slide in the next lecture. So as I have described before only, the making of the brick has several steps. First, the clay is mixed with water, and whatever other minerals are required. You may sometimes feel like there is not enough lime in this one that is required, so you may add a little bit of extra lime. Some iron oxides may be required. You can add that. Then it is molded in the desired shape, dried in the sun, or mechanically. Sometimes you can dry. You can use fans or something to dry it faster. And then these are placed inside a kiln, inside a furnace, and where the temperatures are between 300 and 900 degrees centigrade for several weeks. And what happens during the process is that first the temperatures rise slowly above 100 degrees centigrade, and during that process, water evaporates. Okay, so you should not heat it very quickly, but usually the kilns are very large, and therefore the heating is relatively slow. So any chemical, so there may be water available as a chemically bonded water to the minerals, and there may be free water available, and free water will evaporate very quickly at around 100 degrees centigrade, but chemically bonded water may take up to 600 degrees centigrade to evaporate, because for that the chemical bond has to be broken. Okay, you may remember, right, from your chemistry classes, that water sometimes bonds with minerals chemically. Okay, Then there may be some materials which will oxidize. So there may be some CaCO3, or so there could be some kind of a carbonates or some kind of a sulfates, which may start to oxidize at some point, and they will form CO2 and SO2 gases. They will be required to evaporate, and you should not. That's why you should not have too many of such chemicals, which will lead to a lot of gases evaporating. Because every time a gas is evaporating, that means some void is left behind. Okay, and that usually takes place between 300 and 900 degrees centigrade. Then after 800 degrees centigrade, the most important step takes place, which is vitrification. What is vitrification? As I described before, these small silica particles, these are clay particles, these are sand particles. Once they heat to a certain temperature, about 800 degrees centigrade, and they are touching another particle, they start to fuse together. Okay, these are not really molten. If they were to melt, the brick will lose its shape. But right where they are touching each other, they tend to fuse together, right? Slightly they melt and they just fuse together, and that's how they create an amorphous matrix of silica in a way. And all the other things which are not fused together, they get trapped in this matrix, and as a result, you get a high strength brick. Okay, so this memorize this name, vitrification, and you see, you might have seen the use of this word, vitrified tiles, right? For example, for flooring, often we require vitrified tiles. So you may make tiles without vitrifying them. That is, you don't heat them to that high temperature, but then you don't use such kind of tiles for flooring. For flooring, you would always use vitrified tiles. Vitrified tiles are the high strength tiles. So as a consequence, you get high strength, nicely colored, uniformly colored, free from any cracks, such kind of bricks. Okay, and based on all these properties, we need to characterize these bricks. And in the next class, we will talk about the ways to characterize and classify these bricks, and what are the mechanical properties these bricks need to have, and then based on those mechanical properties, we can classify them. All right, so I think we can stop here today. Let me see if there are any other questions. All right, fine. So guys, we will stop today's discussion here. We will carry on in the next class. Thank you.